And the second one is that this was a 15-minute talk that all of a sudden became a 30-minute talk. So I will try to go a bit deeper than the slides I have. But you guys, please ask me questions because I was trying to keep it short, and now I have a little bit more time. Okay? So, okay. Oh, does this work?
To the left and
Button
right.
on the right.
Button. Oh, this one. Okay, see. Thanks. Okay. So, okay, recently I've been working in this area of self-organization, etc. Let's try to understand what that is. Here are just some examples of self-organization that happens in systems in nature that go from the nanoscale to the macro scale. DNA is a clear example, the way the DNA strings form, and shape has a lot of functionality there. Proteins, the same thing. Wound healing. There's this idea of the school of fish, where these fish come together to fend off predators, whatever it is. And ants are an infinite source of inspiration with all kinds of collective behaviors that emerge without, in a self-organized way. Okay? So if I take this inspiration and I try to think, what could we do if we had some self-organizing nanosensors? Well, the applications are endless, right? I could throw them in an abandoned mine, and they could measure pH or structural integrity, or on a bridge to measure wind, or this is a nuclear reactor and you don't want to send humans in because there's a leak. You could send a bunch of those sensors. They'll find where the leakage is, coat it until humans could come in. And in the health domain, the applications are endless. You could swallow some of these guys that will find some tumor cells, whatever. So that's the vision. But we are going to see in a second where we think we are. Okay, I think, yeah, okay, that's fine. But before I get there, let's try to understand first, especially when we go down to the small scales, what would be some of the challenges that you need to address here. And here I'm talking more about the protein DNA level, this nanosensor idea, which will be very small computational devices, and you have many of them. So, and I believe this thing didn't start. So these guys here are some particle robots that were developed by MIT, Columbia. There's a bunch of universities. They are going to appear later, and I'll have the better disclaimer on which consortium of universities worked on it. And you guys will agree that what those guys can do in this Boston Dynamics spot here is very different. And first of all, at the small scale, you can only assume that you're going to have strictly local sensing and communication, like a one neighborhood communication, and in terms of memory, that you're really going to have a very limited amount of memory per agent, or no memory at all, and that also, that implies that they have to be anonymous. They won't be able to hold an ID. And their movement, if it's self-actuated, is going to be rudimentary and noisy, and even traditional physics may no longer apply at that scale. So that brings us to the notion of what we've been calling programmable matter. And programmable matter, what does that mean? It means I'm going to have an ensemble of many of these tiny computational devices that I'm calling particles. They are going to be active in the sense that they are self-actuated, then they can self-organize. But I'll be able to program what the micro rules that each one of them is going to rule to achieve whatever collective physical properties or behavior that you want. So there's this idea of being programmable, being self-organizing, which leads to the need for local distributed algorithms that each one of them is going to run to achieve the desired collective behavior, et cetera. They should be scalable, so on and so forth. But in this talk, I'm going to try to focus a little bit more about what kind of memories we're going to give to these guys and what we can do with the limitations on memory. So this is just for if some of you are wondering where we stand in this area, because programmable matter is a nice, catchy term, right, that everybody likes. And nanosensors sound amazing, right? I want to swallow some of those. We are not there yet, okay? That's the news. These are some of the systems that are out there. That's the particle robots that you saw earlier. There's some project being done in, there must be a pointer here. Yeah, oh, no, this one. Okay. This is the collaboration between France and CMU a while ago. The kilobots that were originally developed by Radhika Nagpal in Harvard. She's at Princeton now. One of the most developed areas in this arena would be the area of DNA and molecular computing, both on an experimental side and also in the CS theory, where people have derived many models out of this area for, tile self-assembly, et cetera. And here, these are some of two frameworks that were developed by one of my collaborators at MIT, where he develops those robots. They are of colloidal size. He is more or less the scale, 100 micrometers. And these are two platforms. One is the steering micro robots and then these beating particles. I'll talk more about them later, as I'll talk about these Bobots, which, again, was developed with my collaborators at Georgia Tech. I didn't develop any robots, but I worked on the algorithms running on them, okay? Now, I had another slide in a full length talk that talks about the theoretical models that also apply within this arena. I don't have the slide, but population protocols will be one area that relates to all of this. Tile self-assembly, and there have been some others for molecular computing and stuff like that. And the whole area of mobile robots too, for those of you who may be familiar. Why am I not? Okay. And the goal here throughout the talk is that I'm always going to try to pare down the agents as much as I can and understand what's the minimum computation memory requirements that they need to achieve whatever macro behavior I would like them to have. So I'll quickly go through a model so that we have some theoretical model that we can base on, and then we are going to go from there. The Zamibot model is something I developed a while ago with Christian Scheidler. It's a very simple model. I discretize space by using a triangular lattice, could be a square lattice, that doesn't matter, just some discretization. My particles robots live at the nodes of the lattice, and I'm assuming they are anonymous. They have no global orientation or coordinate system or whatsoever. I'm giving them small memory, constant size, and in some cases here I'll talk about when they don't even have that. They have no memory at all that they can play with. This we don't need to worry about right now. They communicate and sense locally, only on the neighbors on this lattice that they have. They can move from a position to another position there, just unoccupied adjacent positions on the grid. And sorry. And this is also not so important for this talk, but just talking about the scheduler that we assume when analyzing some of these algorithms, and that every time they do an action, they do some local computation, and at most one movement.
So it
Yes.
goes one per lattice point?
Yes. Yeah, it's an exclusion process. I can't put two of them. I mean, I could, but for now, let's not put some of them. Okay. So it's a very simple model just to give us some grounds on, what we can say about it. And since we are in a memory management workshop, let's ask ourselves, what could we do with very little memory per agent, constant size memory? We actually have been able to do quite a few things, and here are some examples. This one here is a shape formation algorithm. These particles are going to self-organize and form a triangle that's going to scale up to whatever the size of the system is going to be, and I could do a hexagon and some other simple shapes the same way. More complex shapes we can do too. There's a lot embedded in the algorithm there, but the bottom line is that they are doing all of this just with constant memory per particle and the local sensing, local communication and everything. We were also able to do leader election. I don't have a nice video here for leader election, but this is one of the algorithms that elects a leader at the boundary, and there have been a lot of follow-up, not just by me and collaborators, but other groups also that have worked on this problem. And then we get to things that start becoming a little bit more complex. Here, the guys in black at the center are like some object that I want to coat with my particles in as evenly as possible manner. And if you notice, they were stopped there for a while. They're not really stopped. They're trying to elect a leader using the leader election algorithm. Once they do that, they're able to form layer by layer around the object. Here, I have a very regular hexagon, but this would work even for some other irregular shapes. Okay, so yes.
So, clarification, when you say constant size memory, is that in bits? Constant number of bits or constant number of words?
Bits. Bits, they don't need much. Also, the discretization of space is such that you're always going to have at most 6 neighbors, because right is a grid graph in this case. So even, to know which neighbor to communicate with, you need little memory, and we don't keep much state at all. They don't have IDs, so you don't need to remember that, you don't count. That's what it means.
Do they need to be able to count to 6?
6, yes.
Okay.
Yeah, but that's constant number of bits. Yeah. 6, yes, you're right, they do. They use that when, in many of them, even the leader election one, they count. They're counting angles here, but because the angles you're always incrementing or decrementing by some multiples of 60, you're also okay. You don't need to worry about precision and things like that. Okay? And there's one more slide here. I picked just a few. This is one of the more complex behaviors here, and I think it's hard to see in the video because the particles are so small. But the black guys here, they are some object, and those guys are going to try to build like a convex hull around it, which is going to be the smallest length convex shape that's going to seal the object inside. It's not exactly a convex hull, but something it's a little bit larger than what would be the convex hull that we're thinking of. And this may take a little bit of time to run because this is a more complex algorithm. And one thing nobody asks is why am I saying that these are mostly deterministic? It's just because the structure of the algorithms that they are running here is a deterministic structure, but they do flip a few random bits in the process, in some cases, especially for electing a leader. Okay, but it's not like it's a fully randomized or stochastic algorithm. So here now they're doing their convex hull, and all of this was done as constant size memory. I have a few more examples if people are ready for. I presented a small talk last week on this open problems, and people really liked. I had 2 videos in my talk. They are like, oh, I love the videos. Okay, I decided to really indulge myself here and put as many videos as I can on this one.
It's hypnotic who likes the convex.
Sorry?
Entertaining.
Yeah, I know. And then I have, okay, so I can tell you a little bit more about other things that we have done. Here, these algorithms here, and that's not a video, imagine that. They are also using constant size memory, but they are fully stochastic algorithms where we're keeping no state, and the memory that I need is to compute some of the probabilities that we use in running the algorithm. That's pretty much what it is. They don't have this nice deterministic structure as before. This one here, what I want my particles to do is to start from an arbitrary configuration and gather together, come to a configuration that approximates a disk in terms of perimeter. So these are just some snapshots of the simulation. I'll come back to this problem later, so I decided that too many videos was going to be counter-effective.
So the program running on each node is the same?
Yes. They are identical. They are anonymous. There is no differentiation.
So I'm a little confused. So it's a constant number of bits. So isn't there a constant?
There's a constant number of states. And sometimes we do count to more than a constant number, but we do that by a distributed binary counter that we implement over a string of those guys. Especially in that convex hull wall, we do need that at some point.
So is there a constant number of programs that you can?
Oh, that's probably yes. So you're saying I'm almost exhausting my list here. That's probably true, Raj.
And does the initial state matter, or in your problems you want to put them in some arbitrary state and then do something?
In all of the ones that I showed you, sometimes it does matter. Some of the more complex shape formation ones, we need to start at a reasonably well initialized state. The ones here, let me even see what I had there.
The one where you're surrounding the black, was the black could be an
arbitrary
fixing,
shape, yes.
That doesn't sort of move.
No. That one, as I said, there's this binary counter, this distributed binary counter that we're using there to count some of the length. I didn't describe the whole algorithm in detail. And for the shape formation, we assume that there is a leader there that starts the process, but then I could have elected the leader first, so it depends. I think for the ones here, they don't assume any specific initial configuration. For coating, the only thing I can have, if I have some very narrow tunnels there, then those guys jam up. So that's one assumption, but.
If you don't, is there some assumption about how much of the lattice they cover? Because like any of these, if I have an infinite lattice and I just throw a finite number of points, they may never find each other.
Okay, it's always connected.
It's always connected.
Yeah, it's always connected.
The initial
Yeah.
configuration.
Connected initial configurations, and we keep the system connected at all times to avoid exactly what Phil just described.
Okay.
If they scatter and then you don't have a global coordinate system or orientation
Yeah.
that can guide them, they can just fly away forever. Yeah. Okay, so this was the compression one. I'll talk more about that in a second.
So that doesn't
Okay.
look connected, so. Is
Oh,
that-
it is connected. It's just that the lines are the lines here are just talking about the nearest neighbor edges, like it's just the edges of the lattice that correspond to two neighboring nodes. But if you look here, there is an edge everywhere. Everything's connected. Oh, these are snapshots of the system.
Snapshots.
These are the snapshots of the system. Sorry. Yeah. Okay, so that's one problem. Another one. Okay, sorry. Let me.
Is shape formation a special case? Like, is compression compression and shape formation? It seems like shape formation would solve this.
Yes, you're correct. I could just come here and build a hexagon. I could do that. But the reason why I'm not doing that, there are many reasons. And one of them is robustness of the algorithm. Those algorithms, the stochastic algorithm, they don't keep any state. So provided my system stays connected, you can throw a bomb, you can delete edges, you can do whatever you want. It's going to converge back to that configuration. So we want to exploit those capabilities, especially because eventually in the talk you're going to see that we're going to try to implement this in real robotic systems. And it was important to have algorithms that are simple and yet robust and not keeping a lot of state. But you're right. I could just build a hexagon here and I know how to do it. It would be a perfect disk. Why bother? But that's the reason.
So is there a sort of equivalent to self-stabilization property then?
So self-stabilization, it depends on how you define it here. Self-stabilization usually means that you have a system that's undergoing faults or some kind of changes, and that eventually that's going to stop and your algorithm's going to work. We are not modeling any faults here. I mean, I talked about robustness, but that's just hypothetical in the sense that I'm not assuming any of these particles are faulty and what we do. And this will be self-stabilizing in the sense that for the stochastic algorithms, they would recover naturally from any such faults. There may be some holes in the system because the guy dies there and doesn't move out. Then you have a position there that stays, but the algorithm is not going to break down. Okay. All right, so some other examples here. This one, did it start from the beginning? I don't know anymore. No, it didn't. Okay. Oh, wait. Let me start this again to see. I don't know why it's not starting from the beginning, the animation. Maybe to restart or maybe not. Oh, yes. You saw it started with those three spindly things. And in this problem here, the particles have some colors, and not only want them all to come together, but we want them to separate into clusters of same color classes. Okay? So it's a variant like or an added requirement on that compression problem. So that's another thing that we have done. And then this one's about bridging, and this is just a motivation using some ant bridging example there, and we wanted to replicate this on our particle scenario. There's more on bridging that we have done, but I didn't have nice animations to put here, so I just put this old one. This one's kind of a shortcut bridging, and then some other ones. And then we did something about foraging, and this just means, I talked about this last week, where you have your particles, they're searching space for some food, they find the food, you want them to gather around the food goes away, they go back to searching, but we want to be able to repeat this indefinitely, which becomes more of the challenge here. Doing this once is not a big deal, but I talked about this last week, so I decided not to put any more on this. And there's a last one, just for example here, is this collective locomotion. How do I make the system stay connected and locomote towards a light source? It's some variant of the algorithms here that where they sense the light, the ones that sense the light, they move less. The ones that don't sense the light, they move more. They're at the boundary, they end up coming to the front, and therefore they move towards the light. So those are all examples of things that we can do with constant size memory.
What is the red X around that?
It's just the area. It's just the simulator defines an area. That's how the picture comes out of the simulator. It's nothing important. Okay, the light is this light source here, and then the way this works is that the ones that see the light, they kind of stop, and then the other ones at the boundary, if they keep everything connected, don't have a choice but move around them to the front, and that's how this whole process goes. Okay? All right. Okay, so how about if I give you no memory? What can you do? Yes?
What's the simplest thing it cannot do? But something like, I don't know, organizing things in a square or something like that, where you think it has to really count.
Organize in a square. I can do that.
You can do that? So
I can do
even
that.
equal length?
What I can't do, okay, I'm not going to say I can't do because I haven't proven anything, but shape formation, we can do shapes that are more complex than square, triangle, hexagon. For example, a donut shape or an 8-figure, right? We do have an algorithm that does that. Is much more complex than this one here. It does need some well-initialized state, like a big triangle. But it forms shapes that I can describe. I can have a constant size description of the shape that I can give to the particles. For example, an 8-figure, you can have a constant, like a tiny 8, that you can tell them how it looks like, and they will blow it up and scale it up to the size of the system. But if I have some shape that somehow I don't know how to describe so succinctly, then I don't know how to do it. Okay, because then they'll have to store that information somewhere, maybe distributedly. I just don't know. I'm not saying I can't do, but that's something we don't know how to do. See other things that we tried here, and yes?
What about sort of recursively defined shapes, sort of key graph or?
Fractals, yeah.
Didn't try that one either. But the fractal you can kind of describe with a succinct representation, right? But you have to repeat it, so that repetition as gets bigger, I don't know. That's a good question, yes?
So can you form into a line, I guess?
Yes, a line is easy.
So can you then simulate a Turing machine?
Yes, a bounded state Turing machine, yes. And a lot of the algorithms here haven't, yes.
You said that you basically don't have any lower bounds proving you can't do something. That's just not something you
No,
can.
I don't know it.
Okay.
Any lower bound proofs. If anybody's willing to work on that, that would be amazing, because we haven't even tried to do that. That's not that I can recall. Okay. All right. Okay. Now, who believes that I can do something without memory? Something useful, obviously. Yes, I'm talking. That's right. How would I put the slide and say, "Oh, sorry, guys, just joking, can't do anything"? And I mean, the interpretation of memory is also up for some thinking here, but let's see what do I mean here. So I'm going to go back to that problem that I mentioned before about gathering together, because I'm going to start from this until I can remove the memory and still have the algorithm running, okay? So here I have a system. I want to minimize the perimeter of the system configuration, gather them all together. I am keeping the system connected. For now, I didn't add it to the slide because I didn't want to confuse people, since at some point I will allow things to disconnect. But for now, yes, I am keeping everything connected. And there is a direct trade-off between minimizing the perimeter and maximizing the number of internal edges in the system. That's what this picture there is supposed to represent. And then, given that to minimize the perimeter, you're really trying to increase the number of internal edges of the system, my algorithm is the following. It's going, yes?
What is the input of each particle? I mean, so when you say that constant memory of per particle, so for example, easy case, like I would like to, the shape formation as a triangle, right? Mm-hmm. So what is the input to each particle's constant size memory? What information it holds?
So it depends. To that one, the one that I showed to you, I'm not even giving them the shape. I give them that leader, the guy who starts the process, gives 2 rays. That will be the sides of the triangle. Okay, and they are able to fill that shape in between these 2 rays that they are growing as a snake. Some other shape formation algorithms, the ones especially that handle more complicated shapes, you give a triangle with 3 particles, okay, and they'll try just to, like that's the description, and they'll try to blow up to as big a triangle as the system can accommodate. And what they can see, what do they see as state? They can see where they have neighbors around them, right? And I can assume that they can label their ports in some clockwise or counterclockwise order so that they know, oh, there's a neighbor here in position 1, another one position 2, they must be connected to. So those kinds of things they can infer from the configuration of neighbors.
Can they sense their neighbor's state, or is the information they get from a neighbor less than the state of a neighbor?
They can sense the neighbor state. They can communicate and get their state. This particular class of algorithms, the stochastic ones, this one in particular, sorry, doesn't need that. The one that I was swapping colors, they obviously need to, so the way they combine into color classes, they swap places, so they need to know what color the neighbor has before you can decide to swap or not, things like that. Okay? All right. Okay?
Just to clarify, so in this case, the program for each thing is something like you're in a particular state, you can read the states of your
Yes.
neighbors, and based on that, you can change your state and
Yes.
move.
Yes, exactly.
And that's all you can.
Exactly.
You cannot store anything because you don't have any memories. So you-
Well, have constant size, so you can store.
Well, in this case, you don't have constant.
I said no memory.
Oh, no, I still have. That's what I say. I'm walking towards no memory, okay? For now, I still have, okay? All right, so, okay, can I describe the algorithm that solves this problem here? It's a Markov chain algorithm, and I'm not gonna go in this talk into the nitty-gritty details on how to analyze this Markov chain and what it relates to, etc. But the algorithm boils down to this. All the particles are identical, and all of them will move to a new position with a probability that is proportional to some bias parameter lambda to the power of the difference of the number of edges in the new position and the position they currently are in. Okay? So I'm going to run an example so that everybody understands what exactly I mean here, but I just want you to note a couple of things here. This is an extremely simple algorithm that keeps no state. And
The number of edges means
the number of neighbors, yes, number of neighbors. It can be computed locally because you see how many neighbors you have. Maybe you stick your head and see how many neighbors you're going to have in the new position, but it's a local computation. But I still need memory, right? Because to compute this probability, I need memory. Some constant size memory, but I need memory, okay? But that was the original compression algorithm. And just to make sure everybody's on board, because I know it's easy to say those things, but to understand exactly what they mean sometimes is hard, here's an example.
The number of neighbors is a constant.
It's also constant, yeah, between 0 and 6, yeah. Not 0, because then it'll be disconnected. If you connect it between 1 and 6. Here's this guy, has 2 neighbors right here. He's going to do something that's called an expansion, and I'm going to get out of that later, so don't get too wired up about that. But it's going to look at the position it wants to go to, which is the one on top. It counts 3 neighbors it will have there, and it's going to move to that position with some lambda. Let's say lambda is greater than 1, to the power of 3 minus 2. That gives me probability 1 of moving there, okay? And I'm also ignoring, there's a normalization factor, so those are really probability. I'm abusing notation in a few places here, okay? So that's what it's going to do. It's going to move there because probability 1, it goes there. And the other case is when this guy here had 4 neighbors, tries to move to this new position where to have the 3 green neighbors, and makes the decision to move there with a smaller probability but non-zero, which is going to be my lambda to the power of minus 1, okay? And that's the whole algorithm. And why do I need, so this kind of moves, of course, they hurt me because I'm taking edges out of the system. And if you agree with me that perimeter and number of internal edges, there is a direct relationship between the two of them, I'm moving away from my goal, but it allows me to get out of local minima. That's what this does, okay, in a seamless way.
You separate it? I mean,
No, so remember I said I was preparing a 15-minute talk. I kept on taking slides out of my talk. So there are some local conditions that we can check for maintaining connectivity, but they're local, they're conservative in the sense that there are a lot of times when I could have taken a move and I don't take because I'm not sure if it's going to break connectivity or not, okay? So I didn't describe those because I'm going to move to the disconnected scenario in a second. I just didn't want to.
How do you break the competition for multiple ones wanting to go to the same place?
Okay, so there are 2 answers to your question. The first one, I'm assuming in this, in here, for the analysis of the Markov chain, we assume 1 node is activated at a time. Those are atomic activations. We put the way we interpreting this, like assume each one of them has a Poisson clock. Every time that clock fires, then it decides to do something. The probability that they're going to have two of them firing at the same time is too low. Another way would be that if two of them try to move into a position, one of them wins, the other one goes back. They can't, two nodes cannot move into the same position at the same time, two particles, okay? So, but for the analysis, we analyze the Markov chain as having one move at a time. That's how we look at the evolution of the chain. Okay? All right. Okay, so because this is a theory talk, even if it's a 15-minute talk, I should have a theorem. The reason, and that's why I started with this compression algorithm, because it has a nice, clear description on the results that we achieve. And what we achieve is that if we pick my lambda to be large enough, greater than 2 plus square root of 2, we are going to get at configurations that are an alpha factor away of the minimum perimeter, and we're going to stay there forever from there on. So at stationarity, you're going to be here with all but an exponential small probability, which means that you're going to stay within the class of this alpha compressed configurations for a very long time. Okay? And then not only we could show that, but what was perhaps surprising is that if I pick a lambda that's not large enough, but it's still greater than 1, okay? And then I can pick a constant beta such that for that lambda that I have and the probabilities that I use for the transition matrix of my Markov chain, I'm going to start approximating the maximum perimeter of a configuration, not the minimum one. Have something spindly like what I have on the left there. So it's one algorithm that, depending on where you pick your lambda, you're going to have two different behaviors. Okay? And then, if everybody's okay and believes that I can prove these results, what I'm really going to use later on is that if I allow my system to disconnect, but I keep my region bounded, otherwise what Phil said is completely right. If it's an infinite lattice and I allow it to disconnect, they may just fly forever and never find each other again. I can have a very similar behavior, this phase change behavior, even if we relax connectivity. So here you see that there are some flyaway particles, some holes. And if we eliminate that look ahead that I had, which was convenient for me for the algorithm, but if you start thinking of implementing this on a robot that needs to look at the position it's going to go to, figure out the number of neighbors going to have there, minus the number of neighbors that it has, it starts becoming complicated. So here, the probability, the transition probabilities that we have, we now allow a particle to move to a new position, not based on the difference on the number of neighbors it will have in the new and the old position, but basically just to the power of minus the number of current neighbors it has. So you can think of it as a probability of detachment from the position that is at right now. It turns out that this, I can plug this into the proofs that I had. They use the tail balance, and that still works. And to show that I can relax connectivity, I need some heavier techniques there, but I can prove something very similar than what I had for compression. The reason why I did compression first is that the theorems get more complex here. I have to talk about the region where most of the particles are in that region, forming a cluster that's big. Is not as clean statement as what I had before. Okay? Okay.
So in this area where you have the question mark, if you go do things experimentally, does it do either dispersion or aggregation, or
No,
does it
we
do
don't.
some behavior that's in between and it's neither one?
So what we believe is that for both, this I'm calling aggregation, dispersion, just because I'm disconnecting, it's set to have a different name, or what we had before when everything was connected. We believe there's a sharp phase transition, but we couldn't prove that. Okay? The question mark is just because I didn't put the bounds here because the constants start getting more complex here. But within this bound, like this range here, which is a constant range, we just don't know where that phase transition happens and what exactly is happening there. Okay? Yes?
How fragile are the results with respect to the scheduling? Do you assume in the analysis that it's very nice and uniform?
Yeah,
Is this,
so
is this
yes.
critical?
Well, yes and no. So we don't need uniform probabilities, like picking a particle's probability 1 over n, because just that would be a problem even for the constant size memory that I have. So the way we get around this is what I was saying. We assume that each one of these particles has a Poisson clock with a fixed rate. It could be the same rate for everybody, could be different rates, but they all have a constant rate. And we just allow that Poisson clock to fire. the chance that two of them fire at the exact same time is very small. If we assume that those actions are very fast, they're atomic, then the chance that there is concurrency here is going to be very small. That's the answer to your question. It's a good question, too. So you see, I took out my slides, but you're filling in all the gaps here. That's really good, yeah.
You asked for it.
Okay, all right. Now, okay, what can I say? Oops, something wants to be updated here. All right, so let's try to remove, okay, this is what I was saying. I'm relaxing connectivity and just look ahead, because if I want to implement this in some simple robots, those are unnatural requirements. So we've done that, and let's see what I can do now. All right. So this is what my collaborator at Georgia Tech, Dan Goldman, he's a physicist, an experimental physicist, but he likes to build this, what he calls robophysics, some simple robotic systems to mimic physics behavior, and that's what the platform that he developed. Each one of these bobots about 2 centimeters inside, has some toothbrushes at the bottom that vibrate. That's how they move. It's very noisy movement. There is a CPU here on top that we never use. It's there just because he put it there. And we want to implement that algorithm that allows for dispersion and aggregation on these robots. And what we are going to do, we are going to replace any computation done by the algorithm by placing some magnets on the boundary of the robots. And they are small balls that can rotate. And that's it. We are putting, I think there were 4 of them or six of them to mimic the lattice. And that's all that the robots do. They can move, and they attract each other because they have those magnets, no polarization because those balls can rotate. And that's all that we need to implement the algorithm that I just described to you. Because if you remember that probability that a node moves away from a position where it is, it turned out to be something like the probability of detachment. And it turns out that the way these magnetic forces aggregate around one of the robots, you get the exact equation that I had shown you in the first slide. There's no computation. There's no memory. Maybe you say magnets are memory. You can, I'm up for interpretation of different kinds of memory, but no memory as we know it, no digital algorithm running here. And if you agree with me, there's many leaps from theory, because now I have continuous versus discrete space, noisy but not exactly random motion. The robots are inhomogeneous. Like if you see here, if you leave them alone on this arena, they run in circles, but the circles that they follow are very different from robot to robot. But when you put them all together and we give them magnetic force that's not very large, you see that they just move around. They form some small clusters that disperse, and they keep on doing this forever. However, if we give them magnets that are stronger, you see that they start forming some big clusters that contain almost all of the robots that persist over time. So that's exactly the behavior that we expected to see, that we predicted with the algorithm. But now we're doing it without any computation as we know it. Okay, the magnets are some sort of computation, I get it, but not standard computation, okay? And, okay, looking at this video looks great, but maybe she just cooked up the video so that they look nice and we believe her. But we did, like with the physicists, we did run a bunch of physics simulations, et cetera, to match the predictions of our theoretical model with the GM simulations here. These are the physics-based simulations, and we measured force, we measure effective lambda of the magnets, with respect to what that will correspond in the algorithm, and so on and so forth, to show that there is a match between the algorithm we described and what these robots are doing. Okay? All right. So I hope I convinced you that this has no memory. And okay, so that's what I had about this one. And this work appeared in Science Advances a few years ago. And we are also trying to bring some of these notions to this micro scale with my collaborator, Michael Strano at MIT in chemical engineering. These are some of his systems. This one is a pulsating active matter. These particles all live in a hydrogen peroxide, and the way they do whatever they do is by exposing some metals to the environment and reacting with the environment. This one here, it kind of came for free, that they beat in some very regular patterns here. It's some synchronization that nobody predicted in the system, but exists, and we've been thinking on how to use it. This is just a similar behavior, but now it has, I think this one has 50 particles on it. So you see the behavior is not just so local, like immediate one neighborhood there. You can persist for larger neighborhoods. And this one at the bottom is the one that matches more the kind of stuff that we've been trying to do. It started. These things are moving really slow. I probably should have sped up the video, but I didn't. But if you look, there are some gliders that achieve self-actuated and directed locomotion in this environment, which was an impressive feat from the chemical engineering point of view. So they're moving slowly, but they are moving, and by exposing one side or the other of those two arms that they have, they are able to kind of guide their locomotion.
What's the scale on the bottom right? These are really small things, right?
This is a microscope, right, all of them?
Right.
Now you caught me.
I don't need the exact number, they're really small.
It's comparative to this one, okay? Yeah, they're tiny, small, and they move really slowly, but they are moving, and they have some direction in their movement. So just to conclude here, okay, getting out of this video sometimes. Come on. I don't know why these videos always do this. It's not moving, sorry. Let me stop them, maybe that's what I need to do. Yeah, so these are some of the ideas in this talk. So first was the idea of trying to keep information local, and that allows us to, if you do that, and if you can describe your local environment with a constant amount of information, you can use constant size memory per particle, and then that would allow you to maybe run some algorithms where that's all that you use. This idea of physical embodiment, which is what we call the idea of embedding the algorithm into some physical properties of the robots that you have, allowed you to run the algorithm without any memory as we know it. And then other ideas that we haven't explored yet is the idea of maybe programming the environment, just like ants lay pheromones to guide other ants on, following a path or a trail, et cetera, that we could use the environment to be our memory without having to put the memory on the particles themselves. But just some ideas. And this is a big collaboration that I've had for the past 5 years through AMURI and also some support from NSF. And Michael Strun is the chemical engineer at MIT that does those amazing robots at the tiny little levels. Dan Goldman and Dana Randall are both at Georgia Tech, and they're students and postdocs and collaborators. Sarah graduated there. Christian Scheidler's group in Germany, my own group at ASU, and graduates from that group, Josh Damud, and so on and so forth. And Todd Murphy, he's a mechanical engineer, hybrid control guy at Northwestern. So it has been fun, has been fruitful, and that was all that I had to say. Yes?
It's an impressive
Not
collection
mine.
of collaborators. How did those collaborations come about?
That's a very good question. Remember how I raised my hand and I said that I thought the algorithm in the field program was a great program that worked for us? So it started, I had a sabbatical at Georgia Tech, and I was not going to work with Dana, but I started working with Dana, and I visited this physicist because I knew him or postdocs that he had. So the three of us started working together and got some algorithms in the field grant. That's where the collaboration started. And then there was this call for this DoD MURI proposals, which are big proposals, multidisciplinary, interdisciplinary, and multi-university. And there, the program manager just told us, like the three of us were planning to send something, me, Dana, and Dan, because we're working together. He said, oh, here are these other two guys. Just work with them and write a proposal together. And we're like, okay. One's a chemical engineer, the other one is a mechanical engineer, but it did work. It's a great group, I have to say, has been very rewarding. So, other questions? You guys were very generous because I filled my half an hour easily with all the questions. Yeah.
The Markov chain-based analysis, without going into details. If I take the number of particles in some limit to be very large, and I take like a mean field limit, what does that get me in terms of analytical tractability, and do I get better emergent behavior if I assume some large number of particles?
I don't know the answer to your question. What we proved there's probably a lower bound on how many particles we need to have. I do not remember top of my head, but it's not very large. It's a very simple process. It's like the analysis is based on Glauber dynamics, Metropolis Hastings algorithm, but anyone here who has worked on Markov chains. And it is a variation of this, a lot of this is a variation of this Ising model from statistical physics that we are applying back to algorithm design. So for those of you who know, like will understand a bit more, otherwise there's a talk that I think I'm gonna give in another workshop, and I'll try to go a little bit more deeper into those aspects than I did here. Okay? Yeah, okay, there's,
What's
yeah.
the constant number of states you need for to form the triangles?
Oh my, you guys are really grilling me here. I don't remember top of my head, Kevin, I have to look. I know it's constant, okay, but I don't remember exactly.
I don't think you're supposed to ask other theoreticians what their constants are.
Ask people to wait, you don't ask them about constants.
All right, let's thank the big.
Thank you.
All right, 9 o'clock tomorrow morning.